All right. Hello, everyone. Today, I'm going to run through the lecture on the notes from 4.2, excuse me, precipitation reactions. So we have the definition here. Precipitation reaction is a reaction that results in the formation of an insoluble or solid product. Insoluble means something that does not dissolve in a solvent. Okay. Precipitate is an insoluble solid formed by a reaction in solution. Okay, so the precipitate is the solid that's formed. We talked about this a little bit in Chem 1 when we talked about signs of chemical reactions. I don't know if you guys remember that. It was change in temperature, change in color, the formation of a gas, and then the fourth one was formation of a precipitate. Okay, if you don't recall, I do have so this is a video of a precipitation reaction. So there's two solutions. There's a solution here, the clear liquid in the test tube, and then there's another different clear solution in the dropper in the pipette that's being released into it. Okay. All right. And when they combine, obviously, you get a reaction. So the yellow stuff is actually a solid, and that's the precipitate. Okay, that's the solid that's being formed. And if we let this sit long enough, you would notice that over time the precipitate would settle to the bottom. Okay, the solid would kind of settle to the bottom of it, but that's a precipitation reaction. Okay. All right. So we have an example of a precipitation reaction here. Reaction between lead-2 nitrate and potassium iodide, creating solid lead-2 iodide and aqueous potassium nitrate, which is actually, I think, what that video was. So here's the equation written out. Notice it's important that we're putting the states of matter in. Okay, we've got the aqueous at the beginning, both aqueous, that means solution. So anytime if anything says it's a solution, that means that the state of matter would be aqueous. Okay. The difference between aqueous and liquid is literally the substance in the state of matter of the liquid, whereas aqueous is the substance dissolved in something else, like water. Okay, but we don't put the water there because the water doesn't really affect anything. It's still the substance in the water. It's just kind of in a different mode. So, all right, solubility guideline. Oh, sorry. On the product side of this reaction, you get the PbI2, the solid, this is the precipitate, and then a remaining liquid solution or a remaining solution. Okay. All right. So solubility guidelines. Okay. Trying to reduce the glare a little bit. All right. Solubility guidelines. Solubility is the amount of the substance, okay, at a given temperature that can be dissolved in a given quantity of solvent at the same temperature. So the amount of the substance, this would make this the solute. Okay, that can be dissolved in a given quantity of solvent. Now, excuse me, predicting solubility. One of the things you guys should be able to do by the time we're done with this section is predict if you're given the reactants, if you're given the two reactants, you should be able to predict what the products are going to be. Okay. So now, I don't expect you to know off the top of your head. That's what this table 4.1 on page 125 is for. So here's a copy of it. Okay, I'm gonna put one up on Classroom, but I'm gonna try to make it look a little neater. This is an old copy I have in it. If I have to make a copy of this copy, I don't think it's gonna look real nice. So I'm gonna try to clean it up a little before I post it for you guys. Okay, and it is in your book as well, so you can just go and look there. Okay, so the way this works is soluble means it dissolves in water. Insoluble means it does not. So these would be solid. So actually, and you might even have this written in your book, because I told people in the past that they could write it in there. Okay. Just kind of outlining it so you can see it a little more easily. Okay. All right. So if it's soluble, that means it's aqueous. Okay. If it's insoluble, it means it's going to be a solid. It will not dissolve, won't ionize. Okay. So this top part here, you look at the anion, the negative part. If the anion is on this list, one of these, then the compound is aqueous unless it has this exception with it. So, for example, if the anion in the compound is chlorine, it's going to be an aqueous compound, unless it's like silver chloride or lead 2 chloride. Then those exceptions make it a solid. Okay? The same thing down here for the insoluble ionic compounds, except like flip-flop. So anything with these anions will be insoluble, meaning it's a solid, unless it has these exceptions. If the cation is one of these exceptions, then it would be aqueous. Okay, so anything with sulfide as the anion is going to be a solid, unless it's got ammonium. Anything in the alkali metal cations, alkali metals, so you know, is column 1A, that's these. So any of these would be an exception. Calcium, strontium, and barium. So if the cation has any of these things, that's going to make that compound aqueous. But if it's not, it's a solid. Okay, so let's take a look at the notes and kind of walking through doing this. So to predict solubility, the first thing you do is find the ions from the reactants. Like figure out what the ions are. So from this reactant, we're going to have ions of Mg2 plus and nitrate, NO3 1 minus, right? And then from this one, we're going to have ions of Na plus and OH negative. Okay, so we already know that these two combinations are solutions. They're aqueous. So those aren't a precipitate, obviously. Will a precipitate form? Okay, well, the way to check that is we're going to look at we're essentially going to look at our anions and we're going to combine it with the other cation. So like Mg2 plus, we're going to look at Mg2 plus and OH negative and see what that does. And we're going to look at NO3 negative 1 and Na plus and see what that does. So let's look at the Mg combining with the OH negative. This is essentially like a double replacement reaction. Okay. And we're going to do the Na plus with the NO3 negative. Now, if it's just asking you to figure out if a precipitate will form, you actually don't even need to form the compounds because you're just looking at the comparison. So let's look at Mg and the OH, the hydroxide. So we go to our chart, we look up hydroxide. Hydroxide's down here. So hydroxide is going to be a solid, insoluble solid, unless the cation is one of these exceptions. So our cation is magnesium, right? Is magnesium one of the exceptions for hydroxide? Compounds of the alkali metal cations? No, it's not one of those because it's in, magnesium is here in 2A. NH4, Ca2 plus, Sr2 plus, B8. Okay, no. So magnesium is not an exception. That means this combination is going to produce a precipitate. Okay. Now, just to double check, you shouldn't have, unless something's messed up, you shouldn't have two precipitates because you have an aqueous solution, so you need something to still be in solution, really. You shouldn't get two precipitates, but we can check, and just to help walk through this idea of how we check, let's look at NO3. So NO3 on here is right at the top. NO3 is aqueous unless, oh, there is no unless. Anything combined with nitrate is going to be aqueous. So this is going to be aqueous. All right. So down here at the bottom, we have the precipitation equation all done out. The two reactants, aqueous each, because they're both solutions. They're going to give us products of MgOH2, that's making the compound, crossing the numbers. That's a solid because it's going to precipitate out. And Na and NO3, so Na and NO3, aqueous, and then I just balanced it. Okay, that's how you would predict the solubility and make the equation. Okay. All right. Back of this, of your notes, are a second type of reaction. An exchange or metathesis reaction is a reaction in which the positive ions and negative ions appear to exchange partners. What we called it in chemistry 1 was a double replacement reaction. So this is just the format, excuse me, with the A and the B representing cations and the X and the Y representing anions. Okay. So here's an example. AgNO3 aqueous plus KCl aqueous yields, you get the Ag combining with the Cl, the A, the Y, and the K combining with the NO3. Okay, now one thing that's important to remember, when you do this, you have to put the cation first, the positive, and the anion second. All right? All right. Precipitation reactions and many acid-base reactions will follow this pattern. All right. Ionic equations. A molecular equation is the equation that shows the chemical formulas of the reactants and products without indicating their ionic character. All right, now that sounds weird. What that means is the molecular equation is what we sort of call like just a normal equation. Okay, that's what we're used to looking at and seeing. A complete ionic equation is an equation that shows all soluble strong electrolytes as ions. Okay, it breaks them up. So what has happened here, if you remember back to, let's see our notes in 4.1, here we go, excuse me. Remember when we were showing the ionizing in solution, how this, like the strong electrolytes, break up into positive and negative? Okay. Ionic equations is essentially anything that is aqueous, you are going to split into the ions. Split it into its ions. Okay, so PbNO32 is aqueous. So we're going to split that into Pb2 plus aqueous. Okay, if here. So if I were taking this, I would do PbNO32. It's aqueous, okay? So when this ionizes in the solution, what is it going to look like? Well, it's going to do this, right? Pb2 plus aqueous plus NO3 1 minus aqueous, right? So basically what we want to do is we want to replace in our molecular equation, we want to replace this with this. Okay. So if we look, excuse me, down here, this got replaced with this. Okay, Ki, we split that up because it's aqueous. K plus, I negative 1. Okay, now, on this, I put the coefficients in front. When we're starting out, I usually don't have you guys worry about the coefficients. Okay. Then on the right side, if you look here, PbI2, it's a solid, it's not aqueous. So if you look down here in the complete ionic equation, it is still together. You don't separate that out because it's a solid. You only ionize things that are aqueous. So KNO3 is aqueous, so we split that into the ions. Okay. All right, that is what is called the complete ionic equation. The net ionic equation is the equation showing only the ions and molecules directly involved in the reaction. Something called spectator ions are removed. Spectator ions are ions that appear in identical forms among both the reactants and products of a complete ionic equation. Okay. So, what is this actually talking about? Well, let me zoom out a little so we can hopefully see this. If I were to take this equation, excuse me, and we were to put so I'm going to draw, so the PB, all right. So the PbNO32, if we were to put that into a solution, okay, and the same thing with the Ki. Okay. All right. These are aqueous, right? So, excuse me. What's going to happen is the PbNO32, when it goes in, is going to ionize. So Pb 2 plus and NO3 -1. Okay. So this, when it goes in, is going to split up into the ions. And the same thing is going to happen with the Ki. Right? So the Ki, let's see, what color can I use for it? So the Ki, hopefully this shows up. I haven't tried some of these before. Is also going to ionize because it's aqueous when it's put into the solution. So you've got two separate solutions, right? Okay. When you mix them together, okay, when we mix these together, we essentially are going to have all four of these things, floating around inside of here, right? Well, according to our reaction, what happens? Well, up here, sorry. The Pb and the I2 react together and they form a solid. So we're going to have the PbI2 combining and forming a solid. Sorry, keep on moving. The PbI2 combine and form a solid. What's left over? Well, we have our NO3 combines with the NO3 combines with the K, correct? But it's still aqueous, right? What does that mean? Well, that means it's still dissociated in water. All right. So these are the reactants, right? We've got aqueous PbNO3. We've got aqueous Ki. These are our products. We've got, oh, sorry, I was pointing to one thing here. We've got solid lead 2 iodide and aqueous potassium nitrate, right? Okay, here's where the spectator ion idea comes in. If you look at the difference between this up here and this down here, what's the only thing that's really changed? Well, the only thing that's changed from before the reaction to after is the PbI2. That's become a solid. The K plus 1 and the NO3 negative 1, they were floating around as ions. They were ionized in the solutions before the reaction, right? Well, they're still ionized in the solution after the reaction. So they didn't really do anything. Okay, so the spectator ions are ions that are just, I mean, think about sports, spectators. They just watch the action. They don't actually play or do it. Spectators are things that just watch what's going on, don't actually take part in it. Well, your spectator ions are things that aren't changing from before to after. So our spectator ions are the ones that were ionized before and they're ionized after. They didn't really change. They didn't really do anything. The only things that were actually doing anything were the Pb, the lead, and the iodine. Okay. So what does this lead us to? Well, this brings us to the idea of the net ionic equation. The net ionic equation is essentially the complete ionic equation with the spectator ions removed. Okay, so what did we say were the spectator ions for this one? We said the spectator ions were K plus and NO3 negative 1, right? So let's go up here to our complete ionic and let's identify those. The NO3 and the K plus. Right? Same thing over here. Okay. Now, how do you know this without doing like the diagram like the drawn out diagram that I did? Well, essentially, the spectator ions are identical on both sides. They're the same. NO3 negative 1 aqueous, NO3 negative 1 aqueous. K plus aqueous, K plus aqueous. If you look, you've got like Pb2 plus aqueous over here. You don't have a Pb2 plus aqueous over here. So that's not a spectator ion. Okay? All right. So if you pull those out, if you take those out of the equation, what do you end up with? Well, you end up with the net ionic equation. It's everything else. Pb2 plus aqueous, Pb2 plus aqueous. 2i negative 1 aqueous, 2i negative 1 aqueous. Yields PbI2 solid, PbI2 solid. It's just the complete ionic minus the spectators. Okay. All right. This demonstrates that more than one set of reactants can lead to the same net reaction. We're not going to worry about that too much right now. I will show you that at a later point. Okay, that idea. Okay, I'm going to stop here because this is a really long video already. Um, I might do another video where I run through some more examples of these just to help you guys out as well, but that'll come a little later. Okay, again, as usual, if you guys have questions, please let me know. Use Remind, Google Classroom, whatever. Okay, have a good one.